Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll continue our discussion on the Laplacian flows. In particular, we'll focus on deriving the solution of the Laplacian flows. In the process of solving it, we'll eventually prove during the lectures that this solution actually depends on the exponential of the negative of the Laplacian matrix. So this exponential also has a lot of nice properties, which will be the focus of today's lecture. So let's get started.
Let's start by doing a quick recap of a formula that we'll be using in today's lecture. Consider a time invariant matrix L. Then L and its exponential given by e raised to the power LT commute. So what does it mean? It means that e raised to the power LT times L is the same as L times e raised to the power t. Why does it hold? Let's quickly see. E raised to the power LT can simply be written as, we do the expansion that we are familiar with, L squared by 2 factorial t squared, and so on, multiplied by L. Let's multiply all of the terms here with L. And what do we get then? L squared t plus L cubed divided by 2 factorial times t squared, and so on. Notice that what we can do here is we can again take L common, but now on the left. So we write I plus LT plus L squared divided by 2 factorial times t squared, and so on. Hence, what we get here is L, and this entire thing is nothing but the matrix exponential again. So e raised to the power LT. Hence, we have shown here that L and e raised to the power LT actually commute. Okay. Now let's come to the main focus of today's lecture, which is the solution of a Laplacian flow. How does a Laplacian flow evolve over time? So let's make this subheading here now. Let's start. We know that for a digraph G and its corresponding Laplacian matrix L, the Laplacian flow is given by x naught equals minus Lx. That's it. So we are interested in figuring out, okay, if you want to be a bit more precise while writing this, what we can do is, we can write here x dot of t and x of t. And we've been given some initial conditions, x0. Note that here x is an n cross 1 vector corresponding to the states of all of the nodes, where x is the n cross 1 vector of the states of all the agents in the network. And n, the n that is given here, is obviously nothing but the number of nodes, number of agents in the network, or equivalently, the number of nodes in G. Okay. This is the framework that we have. In this framework, we try to now understand if the system starts at some initial condition x0. As time progresses, how does x of t vary with time? Meaning, we only have to look at the solution of this very simple differential equation. What our primary objective will be is to see if we can apply any graph theoretic notions to the solution that we get here to get some insights into additional properties that the Laplacian flow might have. Meaning, do the solutions of some of the agents, meaning to the states of some of the agents, evolve towards the state of one of the agents in the network? Meaning, does one of the agents here act as a leader, or perhaps multiple of them act as leaders for a different set of agents in the network? How do we figure out the answers to these questions? That will be the main focus of today's lecture. But before we get to that, we'll first write out the simple solution of this differential equation. So let's do that first. We start by x dot of t is given as being equal to L times x of t. Let us left multiply e raised to the power Lt on both sides. And what we can do is we can bring this to the LHS. Hence, we will write e raised to the power Lt, L times x of t equals 0. Okay. Now again, what we can do is we can further rearrange this a little bit by writing the first term remains as it is, but now on the second term, we make, since now we already know that e raised to the power Lt and L actually commute. This is something we saw at the beginning of the lecture. E raised to the power Lt times L is the same as L times e raised to the power Lt. Meaning, now we can write this. Notice that this expression is nothing but the same as this times x of t. Hence, we can now do an integration on both sides. dt runs from 0 to t. Again, we write the integration on the RHS too. What exactly is the solution now? Upon integrating, let's add some number to it, say 1. Upon integrating equation number 1, we simply get x of t. So it's a definite integral. So let's say we write it as e to the power Lt running from 0 to t here. And this continues to be 0. So this is equal to e raised to the power Lt times x of t minus of e raised to the power 0, which simply becomes identity, so it doesn't matter. So x of 0 being equal to 0, hence the final solution becomes x of t as being equal to e raised to the power minus of LT times x of 0. This is the solution of our Laplacian flow. So we can observe a few interesting things here. Notice here that the entire solution depends only on the term e raised to the power minus LT, meaning we can now say for the system x dot of t equals minus of L x of t, the properties of stability and consensus, in fact, any of the properties dependent on the states of the system, depend on the exponential e raised to the power minus LT. Hence, if you want to figure out whether the system is stable or not, all that we need to do is observe this. Again, if we want to look at whether or not we achieve consensus, somehow we have to show that e raised to the power minus LT must have some nice properties which can actually drive the system to consensus. Notice here that all of the x zeros need not start at the same value, meaning all of the entries here may not be the same. Still, if you want to achieve consensus, then somehow e raised to the power minus LT, when multiplied with this, should give us a vector, all of whose entries are the same, meaning that we have achieved consensus. So what are the properties that can be associated with this matrix e raised to the power minus LT? Let us try to look at some of its properties. Next, we look at the properties of e raised to the power minus LT. Just to remind us, let L be the Laplacian matrix of a digraph G containing n nodes, n number of nodes. Furthermore, in order to easily derive the properties, we introduced a term L max. What is L max? L max is simply equal to the maximum over all the diagonal entries of the Laplacian, meaning L11, L22 up to L and n. Okay, with this, we are now ready to state all of the properties. Let's start with the first property. The first property says that e raised to the power minus L is a row stochastic matrix. Again, what is a row stochastic matrix? We know that a matrix is row stochastic if all of its entries are non-negative. Additionally, all of its row sums add up to 1. So let's start with a quick proof. We already know that L times 1n is equal to 0n. So we're going to use this property in order to prove that e to the power minus L is row stochastic. How? Since the row sums of L add up to 0, when we multiply 1 and 2 it, we know that it gives us a vector of all the row sums. Hence, if you're interested in adding up all of the rows of e raised to the power minus l, again, we should multiply it with the vector 1n. In order to evaluate the row sums of e raised to the power minus l, we do the following. We multiply it with 1n and try to calculate what this product is going to be. And this is really straightforward now. Again, we can write a power series expansion of e raised to the power minus l as in. Why in? We know that the L that we have here L matrix that we have is actually n cross n because the underlying digraph has n number of nodes. Okay, so then I can write here in. And then similarly, the second term will be L times, okay, just L plus L squared divided by 2 factorial. So on and so forth. And we multiply 1 into it. So we take this 1n inside this bracket. Then we get in times 1n is simply 1n. And we have L times 1n plus L squared by 2 factorial times 1n and so on. Notice that L times 1n, as we see here, is simply equal to 0. Hence, this evaluates to 0. If we look at this term, L squared divided by 2 factorial times 1n, I can write this as L by 2 factorial multiplied by L into 1n. L into 1n again evaluates to 0. Hence, we have L times the 0 vector divided by 2 factorial, which simply evaluates to, again, anything multiplied with the 0 vector gives us the 0 vector only. Hence, we have 0n here. Notice that the same logic can be applied to every other term that appears, meaning this evaluates to 0. All the other terms also evaluate to 0. So what we are effectively left with is, this implies that e raised to the power minus l times 1n is simply equal to 1n. What does this mean? This directly means that e raised to the power minus l is row stochastic. So we showed that the row sums are equal to 1. However, row stochasticity needs yet another property of non-negativity of all of the entries. So I leave it for all of you to verify whether or not the entries of e raised to the power minus l are non-negative. Okay, let's look at the second property. The second property says that consider G to be weight balanced. Then 1n transpose e raised to the power minus l adds up to 1n transpose, or is this product is equal to 1n transpose. What does this imply? This implies that e raised to the power minus l is now also column stochastic. Let me highlight something before we look at the proof. The first condition applies to every e raised to the power minus l, meaning every e raised to the power minus l is row stochastic. Now, additionally, when the digraph is weight balanced, as shown here, then e raised to the power minus l becomes also column stochastic. So the proof of this again is very simple. Let's quickly look at it. Then we know that for weight balance networks, we have 1 n transpose times L adding up to the 0 n vector. Why? Because since it is weight graph, for every node the in degree equals the out degree. Hence, that boils down to this condition. The proof of this was actually discussed when we were looking at the Laplacian matrices. Continuing with this, then let us now evaluate the column sums of e raised to the power minus L. The column sums of e raised to the power minus L can be similarly evaluated as one n transpose e raised to the power minus L. Again, we do the same things that we did for the previous proof. We write the power series expansion, so on. So this evaluates to the following. We now multiply 1 n transpose and take it inside this bracket post multiplication. So the first term simply becomes equal to 1 n transpose, and the second term is 1 n transpose L. Again, 1 n transpose L square, where 2 factorial, and so on. Now, it follows directly from the proof that we did for the previous property. We know that as given, since it is a weight balance digraph, we already know that 1 n transpose L becomes equal to 0 n vector. Hence, all of the other terms also evaluate to 0, meaning what we are left with is, this implies 1 n transpose e raised to the power minus L is actually equal to 1 n transpose, meaning that e raised to the power minus L is column stochastic. Again, remember that one still needs to show that all of the entries of e raised to the power minus L are non-negative. The third property is the following. It says that e raised to the power minus L is always greater than or equal to e raised to the power minus L max times In, which again is of course greater than or equal to 0. So just to remind you, L max here is the maximum of all the diagonal entries of the Laplacian. This is L max. So now let's look at the proof of this property. So this is slightly more detailed than the previous two proofs that we saw before. With this, we end today's lecture. In the next lecture, we'll continue discussing the properties associated with the exponential of the Laplacian. Thank you.